Okay, what I want to point out is this is just a simple problem of essentially the sum of the forces equals 0 in a static situation. So you've got a flow of water coming in and basically dissipating all its momentum onto this wall, and this force from the other side is balancing the force of the water. So the sum of the forces is going to equal 0. Or another way of saying that is the force going to the left is equal to the force of the water going to the right. And it's equal to the mass times the acceleration, or mass times the change in volume per time, or kind of moving this over here because we know that, not change in volume, I'm sorry, change in velocity per time. We can also write that mass per time times the change in velocity. Really what's happening is the velocity is going from whatever the velocity is when it hits the thing to 0. So it's going from this value to 0. So that would be the change in velocity. And the mass, change in mass per time is really basically the mass flow rate that's coming out of this hose. So you see this in the FE materials. Let's see if I can pull that up. If we scroll down here, there's an equation that represents it, the impulse momentum principle. So what we're dealing with here is basically the flow Q times the density, the volumetric flow rate times the density times the velocity 2 minus the velocity 1. So let's just deal with that equation. So get back to here. Oops. So we have the sum of the forces is equal to Q2 density 2 V2 minus Q1 rho 2 V1. So we know in our situation the initial velocity is whatever the velocity is here, and the final velocity is essentially 0. We're losing all the velocity. So we've got in this equation the force, really the only force that we have here, is equal to negative Q1 rho 2 V1. And I suppose if we called this the plus A, this is not responding to my stylus. If we called this the plus X direction, this would be a negative force here. So we can just kind of neglect this negative sign, and we know that the magnitude of this force is going to be equal to the Q times the density times the velocity. So let's go ahead and work that out. So this is equal to the flow rate, 0.05 meters cubed per second, times the density, 1,000 kilograms per meter cubed, times the velocity. Now, how the heck are we going to get the velocity? Well, we know that the velocity comes from the water, the volumetric flow rate here. If we can look at, I guess I will say I can just reason this out. Q is equal to the area times the velocity. So this is going to be meters squared times meters per second, and that was going to give me meters cubed per second. So in other words, the velocity is equal to Q divided by the area, and I could put that into my equation up here for, I guess, for velocity. So it's equal to Q, 0.05 meters cubed per second, divided by the area, which is going to be pi over 4 times the diameter squared, which is in meters. The diameter is up here. Over here is 0.1 meters squared. 0.1 meters. You can't see that squared. I'm going to take this whole set of equations and take it to the next page, if I can remember that. Okay. the force is equal to 0.05 meters cubed per second times 1,000 kilograms per meter cubed times 0.05 meters cubed per second. That's Q divided by the area, 1 over pi over 4, I'm going to bring the 4 up here, times the diameter squared, 0.1 meter squared. Okay, now I'm going to start with the units because I love units. They're so helpful to keep track of them. So we've got meters cubed canceling here. I'm going to have meters squared on the bottom here and meters cubed on the top. So I'm going to end up getting kilogram meters per second. Is that right? Seconds times second squared. Kilogram meters per second squared, which we know is a Newton. Hooray! We've gotten the force in terms of newtons. So let's just do the math here then. So we've got 0.05 times 1,000 times 0.05 times 4 over pi times 0.1 times 0.1. So let's see, I'm going to move some decimal places around here. I'm going to move these 1, 2 decimal places, so I'm going to get rid of 2 zeros, and then another 0. I'm going to move this 1 decimal place. So we have 5 times 4 is 20 times 0.5 is, that's 20, half of 5.5, 20 is 10. So we have 10 on the top. And on the bottom we have 10, let's see, divided by 0.1 is like times 10. So that's 100. And then times 10 again is 1,000 over pi is, like a little over 3 or so. We know that that's going to be about, I don't know, 320, about 320 newtons is the force. And that would be the force required to keep the plate vertical.